Welcome back. So previously we've talked a bit about having a normal population that you're sampling from to try to determine the mean. And we looked at this in particular in the case where we assumed that we understood the standard deviation of the population. This is a big ask, of course. But so the question naturally comes up. I mean, we have this way of approximating the standard deviation of the population by using the square root of the sample variance, this capital S or capital S squared. So the question naturally arises, what if we simply substituted the population variance for the sample variance in the formula? So let's be a little bit more concrete. All right, so suppose you have a normally distributed population with a known variance and an unknown mean. Then this thing is a standard normal random variable, which we usually refer to as z. And so what that tells us is if we know this sigma, we can use this pretty effectively to get intervals, confidence intervals for mu. So cutting to the chase, knowing that we have a standard normal random variable with this particular combination, and we know that there's a 95% certainty that a standard normal variable is between -2 and 2. If we substitute in and rearrange, we get this expression right here, and that gives us a 95% confidence interval for the mean, the population mean. So the question is, what if we just look at x bar minus mu over, instead of sigma over root n, how about s over root n? So s being the square root of s squared, the sample variance, this is just the sum of the xi's minus x bar over n minus 1. And this is supposed to be a reasonable estimate of the population variance, and so s is a reasonable estimate of the population standard deviation. And so the question is this normal? Is that a unit normal random variable, standard normal random variable? If so, we could do the same interval estimates, but it's not normal. Not actually normal. We'll see that it behaves normally if n is relatively large, but only in a certain limited sense. But do we give up? No, we do not give up. It's not normal, but it's something else, and the point is we can understand what it is. So it turns out that this particular combination, x minus mu over s divided by root n, is a random variable with the so-called t distribution. So fortunately, this distribution is well studied, and we can use the fact that we can look up values of the t-distribution to actually get confidence intervals for the mean, even if we don't have the standard deviation. The important thing to keep in mind, though, is that this is just a different distribution. It's not the standard normal random variable. T-distribution, I should say, with n minus 1 degrees of freedom. And as n gets large, this will approach the standard normal random variable. Okay, so let's take a look at the t-distribution. All right, so the t-distribution has this easy to remember shape. It is the form f of t is the gamma function of k plus 1 over 2 divided by pi k gamma of k over 2 times 1 plus t squared over k, quantity raised to the power k plus 1 over 2. This is where k is the number of degrees of freedom. And this is kind of a mouthful, of course, but most of this is kind of just the normalization factors. So if we wanted to be rough about this, we could just say this is proportional to really 1 over 1 plus k inverse t squared to the power of half of k plus 1. And you can see just in this like a really essentially different qualitative feature of this distribution from the standard normal distribution. Well, so the normal distribution is very roughly e to the minus x squared. This thing decays super fast, 1 over e to the x squared. E to the x squared, grows super quickly, exponential with a square inside of it. Whereas this thing, for large x, this distribution, this probability density function, looks something like 1 over x to the k plus 1. If x was our variable, we're calling it t for sociological reasons. Okay, so 1 over x to the k plus 1, that decays, not super fast. It's a polynomial kind of growth, this x to the k plus 1. This thing, the normal distribution has this like exponential action in there. What that means is that the distribution is fat on the edges. It doesn't go close to 0 very quickly, right? So whereas the normal distribution goes really kind of tightly down, hugging the graph, this one is a little thicker. It does. Oh, I don't know what it does, but it just doesn't decay so quickly on the outside. What that means, practical purposes, if you're trying to make confidence intervals, you might not see it so much, for your medium-sized k if you're looking at a 90% confidence interval, but when you're trying to get like the 99.9% percent confidence intervals, you're going to be feeling those fat tails off on the edge pretty far, because they're because it decays slowly as you go further out. It's hard to eliminate those things happening. There's still some reasonable probability that doesn't get small super quick that you're going to be way out off in the horizon, right? So that's the difference. Alright, so let's take a look at an example. Now, suppose we're trying to figure out... Okay, so let's take a look at an example. Suppose there's some population, and with, I don't know, maybe there are lengths of screws in a box or something like that. And but we're going to assume that it's normally distributed. So, normal population. And somebody gives us a claim about what the mean value is in that population, what the mean is. So the claim is that the population mean is, 20. Okay, so 20 millimeters is the typical length of one of these screws, they claim. And we want to test that. So what do? We close our eyes, we reach into a box of these screws, we grab, say, 6 screws. We sample with n equals 6, and we measure a sample mean of, let's say, 21, and a sample, let's say, standard deviation of 1, for example. Okay. So the question is, can we determine whether or not we think they're correct with this population? Do we think it really could be 20? How likely is that? So let's take a look. The point here is that if we look at this random variable, x bar minus the population mean divided by the sample standard deviation divided by n, this is a variable with a t-distribution. And in the case that we're interested in, n is equal to 6. This has 5 degrees of freedom. And let's see, so in particular, what do we do? What did we just do? We measured that x bar was 21. We're claiming the population mean is 20. And we have 1 divided by the square root of 6. There we go. So that's 1 divided by 1 over square root of 6, which is square root of 6. Square root of 6 is, I don't know, it's like a little more than 2. I don't know, 2.3-ish. I guess I could figure that out. And now we'd like to know, well, what are we wondering? Well, x bar, if we look at this, x bar is bigger than the claim. So we're wondering, like, this variable, which should be 0, it should be centered around 0, is not 0, it's to the right of 0 by 2.3. Now, if we think about this, if this was a normal distribution here, then 2.3, that's 2 standard deviations out. That would be like a very unlikely thing to happen. We have less certainty here, probably, because we're looking at a t-distribution. So to see how likely this is, let's go ahead and look this up on a chart. So here's a table for values of the t-distribution. What we can see here is that if we are about 2.3 out, so really, what are we saying? Where this chart is saying, if you give one of these, how do we read this chart? We are looking at 5 degrees of freedom, so we're here in this row. And what this chart tells us is that with probability 0.1, we're above this value, probability 0.05 above this value, probability of this, we're above this value. Okay, so this is basically telling us how big these tails are off to the right. That's really what these are measuring. If we were to draw if I was to draw one of these t-distributions, we're saying this 1.476 is the place where the area under the curve here is 0.1, and over here at 2, this is the place where the area is 0.05. Okay, and just by way of comparison, by the time you get out to about 2 with the standard normal distribution, you have about 0.025 in there, right? Because 5% on either side. If you're looking at 5% on either side when you get to from -2 to 2 in the normal distribution. Okay, 0.025 on either side. So you can see the tail here is about twice as fat when you got 2 out than it was for the standard normal. All right, so in any case, in our particular example, we're saying, how likely is it that we're over here about 2.3 out? Well, you can see on the chart, it doesn't have 2.3, but that's somewhere in between here and there. So the probability is somewhere between 0.025 and 0.5, or in other words, the probability is something like, so it's between 2.5% and 5% that we made these measurements. And so if you're trying to figure out whether or not you should have believed this person, that this claim that the population mean was 20, well, looks likely that it's false. Only a 2.5 to 5% chance that made sense based on the observation. You can imagine how would this have changed if instead of having n equals 6, we had n equals, let's say, 10, for example. Let me just make the changes like this. So if this was actually a 10, so you'd have 9 degrees of freedom, and this thing is a 10, and the value would have been, so that's root 10, which is more like 3. And if we're over here at 9 degrees of freedom, and we have a measured value of about 3, then we're getting pretty close to, over here, to the 0.5% zone. So there would have only been a 0.5% chance of measuring our values of x bar being, 21, and s being 1 if mu was equal to 20. Okay, so that would have been a pretty unlikely thing. And there we go.